So let's go ahead and get started. So we're actually getting into very, very interesting territory in the sense that we can begin to see the forest from the trees and the things that we're talking about now. So as we went through the semester, things might have seemed a little bit disconnected, or why is it that I do Gauss's law and then circuit analysis, the magnetic fields. But now what we're getting into allows us to really appreciate how all of these things come together in a more meaningful way. But before I even talk about that, I want to talk about something that I mentioned in the notes at the very beginning, and that's three principles of what theory means for physics in particular and science in general. So the first thing that's really important for theory is that it's experimentally testable and falsifiable. So you can do experiments, for instance, to show that Faraday's law is true, but you can also come up with ideas or experiments that might show that the theory is wrong, and then you'd have to modify the theory or come up with another theory. A second principle that's very important for physical theory is that it makes predictions. So you come up with an idea and it satisfies things that you know already, but it also allows you to make predictions about something else. That's something that we haven't quite seen yet, but as we're getting into the wave equation, that's really that aspect of theory is going to be coming into play, because when Maxwell united all of what are now called Maxwell's equations, he was able to make predictions about the wave nature of light. The third and final thing about theory that's important is that it recovers results that are previously known. And again, when we're looking at the wave equation, we end up seeing this funny term that comes out of it in the end, that V is equal to the square root of mu naught times epsilon naught. This is, when you plug in the values for this gives you something that says this is 3 times 10 to the 8th meters per second. And this is the speed of light. And what's interesting about this and why it recovers things that were already known is because the speed of light was measured before Maxwell did his work and came to the wave equation. So this actually recovered something that had existed already. It pointed to why Maxwell's equations really give a very accurate description of reality. So for the homework, what we're going to be doing is going through the derivation of the wave equation. But before that, the theory was kind of in trouble because, as we saw in the homework, Ampere's law was incomplete, and it was falsifiable in the sense that Maxwell was able to come up with a thought experiment that showed an exception. And that exception was, if you consider some infinitely long current-carrying wire with current I, and we want to find what the magnetic field is. Well, we've seen this plenty of times. You just apply Ampere's law here. So you say the integral of B dot dl is equal to mu naught times I in. Okay, pretty standard calculation that we've done so far. But what Maxwell pondered was, well, what happens if I put a capacitor here and I say I have this setup, and I want to find what the magnetic field is between the plates of the capacitor. So when we were doing this before, we would draw some Amperian loop like this. Here we would draw an Amperian loop like this. So looking at this, and again we have this current that's flowing to and from the plates of the capacitor. Looking at this and thinking about what Biot-Savart says, we know that we could define some infinitesimal element. So remind you that Biot-Savart said dB is equal to mu naught divided by 4 pi I dl cross r hat divided by r squared. So we can define all of these things in this equation. So we have our dl, we have our r hat, there's some r, and we can do this calculation, and Biot-Savart says that there should be a magnetic field here, but Ampere doesn't, right? Because if we think about what the current is that flows through this loop, there's not going to be any current moving from one plate of the capacitor to the other, right? The current can only flow through the wire. And so because of that, when you try to calculate the magnetic field with Ampere's law as written, you get 0. And that's a problem because we know that we shouldn't have a magnetic field of 0 here. And so what Maxwell did was he said, well, Faraday's law says that there's a relationship between the electric field and the magnetic field such that a time-dependent magnetic flux will induce an electric field. What if a time-dependent electric flux can induce a magnetic field? And so what he did was he added an additional term to Ampere's law. And the term that he added was a plus mu naught epsilon naught partial derivative with respect to time integral E dot dA. So again, you can kind of compare this to the way that Faraday's law looks. So Faraday's law says the integral of E dot dL is equal to minus partial derivative with respect to time integral of B dot dA. And comparing this term to this term, they look very similar, right? It's just a difference of the field that you're putting in. And this was probably one of the first really important, Maxwell actually was the one that formulated Faraday's law. There's historical reasons why we call it Faraday's law, but Maxwell was the one that wrote it down. Faraday was an experimentalist, and he showed tabletop experiments to show the relationship between B and E, but Maxwell was actually the one that wrote down this equation. Yeah?
Probably not that important, but what's the difference between mu naught and epsilon naught? I know they're both permeabilities of free space.
Sure. So this one's the permeability of free space. Mu naught is the permeability of free space. Epsilon naught is the permittivity of free space. Okay. And so, yeah, epsilon naught. The first time we encountered epsilon naught was when we were writing down Coulomb's law, right? So force between two charges. Right, that's epsilon naught. And it says something about the way that an electric field propagates in a vacuum. Mu naught says something about how a magnetic field propagates in a vacuum. But again, when you look at this, you say, well, it's really strange and in a way wonderful that when you look at what Maxwell derived here, these two seemingly unrelated quantities, one has to do with the magnetic field, one has to do with an electric field, combine together to point to the speed of light. It's not something that you would naturally expect to happen, but this is the way that nature is, and part of the reason why this is really interesting, that you wouldn't expect these two parameters to talk to each other in this way, but they talk to each other in a way that point to something else, and that's the speed of light. Okay. So any questions about this? This is kind of overview kind of stuff. Yeah.
So when you're looking at the dA, is the area? What area is that? Is it just the area inside some loop that is where you're evaluating, finding the magnetic field at, or?
This is so in this equation.
Yeah.
So this area, and there's some caveats here because it's just it's the area that's bounded by the loop. Mm-hmm. And we've always said that this is just some flat area, right? So that's what the area is. It's the area that the electric field is passing through.
So the DL is going to be the distance around a circle at some arm.
Right.
And the area is going to be the area contained within that.
Exactly. Now, something that I kind of swept under the rug a little bit was, we're assuming that this is a flat surface. It actually doesn't have to be. Faraday's law and the Ampere-Maxwell equation are still true if this isn't a flat surface, but then that kind of gives us something else to think about, because this could be like a trash bag, right? Trash bag is bound by its rim, but it has an area that the rest of the bag makes up, and it's not flat, but you can extend it out here, and Ampere's law needs to be true, regardless of if I have the loop that's flat or the trash bag surface. But when I look at this, what current goes through this surface? It's the current actually that's going through the wire. But that's inconsistent with what I would have for the flat loop, right? And it shouldn't matter whether I have this flat surface or if I have this kind of trash bag surface.
Isn't it the same amount of current passing through it, or I guess I don't understand.
Because the point is here, there is no current that flows through this.
Okay, right.
Because there's no there's no current that flows from the plate, this plate to this plate. There is something else that flows, and that's the electric field.
Okay.
And that's ultimately why Maxwell did this, was he said, well, there's no current that flows through this loop here. There is an electric field. How can I say something about how that electric field is changing and flowing through this loop and give me the same answer that I would expect if I didn't have the capacitor at all?
So just as like a rough intuition, is the magnetic field, if you were to go between and around that capacitor, is it going to be the same as it would be in the wire?
Yeah.
And that's surprising, because you would think that it would be different, some sort of a magnetic anomaly there or a bubble.
Well, sure. I'm sweeping some things under the rug. For instance, that there are fringe fields on the edge here, and it doesn't point exactly left to right. So there's some approximations that I'm making here. But ultimately, you can think about it, because say the capacitor is really small, like really, really small. And you compare that on a macro scale to what, you compare what the magnetic field should look like in that case to this case, they should look the same, right?
Yeah.
Yeah, and there might be some differences based on some geometry and the fact that it's not a perfect approximation, but they should look very similar. Yeah. Other questions? So what we're going to go through today is to actually apply Gauss's law between these two plates of the capacitor to find what the electric field is explicitly, and show that when I do that, it gives me the same answer as if the capacitor wasn't there at all. Okay? So go ahead and get started on that, and I'll come around and answer questions as you guys have them. I also updated the notes like a minute before class, because I didn't realize I didn't do that again last night, but the notes that include the wave equation are on there now too.